Okay, so let's talk about some of these problems. On problem 39, you've got, this is just more, you have to look up data and do stuff with it. So, on 39 it says, what's the gravitational force of the sun on the earth? So the only thing you can do on 39 is start with the idea that centripetal force equals big G, mass of the earth, mass of the sun, over distance squared. It's just smash mouth physics. Okay, there's nothing clever you can do. You just have to get that number. Okay? Go to the back of the book, that table A7, you can find the mass of the sun, you can find the mass of the earth, and use the distance in between the two of them. Okay? So that first answer on 39A should be something times 10 to the 22nd. Okay, that's a big number, right? Then, on B, what's the gravitational force of the moon on the earth? This is why we have tides. Because as our rock is going around the sun, the moon is going with it, okay? So, with that one, then you're looking at going, okay, what's the gravitational attraction between these two objects, which should be something times 10 to the 20th, okay? And then it says, what moon's force is what percentage of the sun's force? So that should be a very small number, okay, that asks for a percentage. So to get your answer to 39C, basically take your answer from 39B, divide it by your answer to 39A, multiply it by 100. There's nothing clever, that's just smash mouth physics, okay? That's all there is to it. On 38, with this one, you're told that Kepler 39b has a diameter that is 1.2 times that of Jupiter, but a mass that is 18 times that of Jupiter. What would be the period of the satellite in low orbit around this large, dense planet? So basically on that one, you're just going to go to that 4 pi squared r cubed. You just have to find the mass and diameter of Jupiter and do smash mouth physics. So your answer to 38 in seconds would make a not so good, not horrible, but not bad GPA times 10 to the third. Okay? Like that, Charles? Okay. Now,
that's a great GPA.
Let's talk about problem 48 out of the book, because this gets a little bit weird. Not bad, but a little bit. So on 48,
what up, Nick?
Oh, pretty sure I have a calculator in here.
Yeah, I the calculator, you left some paperwork.
Okay, well, like what we said, what brings it
okay. So here's what you got to do on 48. So if you look on this one, HD orbits with a period of 600 days at a distance of 1.4 AU from its star. What's the ratio of the star's mass to our sun's mass? So this is very relevant to what's happening in astronomy now, because we launched a satellite, it's actually called Kepler. And its whole point is to find exoplanets. And exoplanets, search for those is actually incredibly difficult, mainly because of the distances that are involved. So a lot of times what they'll do is they'll look at a light coming from a distant star. And like I said, the nearest star is like Proxima Centaurus, which is like 3 and some odd change light years away, and that's the closest one. So the vast majority of space is space. So if what they would do to figure out, okay, hey, are there planets orbiting, because you really can't necessarily, usually you can't even see the planet itself. So what you would do is that you would monitor how much light is being emitted from this particular sun or star, depending on what you would call it. And then when a planet would go in front of it, what would happen is that that would become dimmed just a little bit. So imagine like there's a candle 100 yards away. And then every once in a while, like a ping pong ball would go between that candle and you. So when that ping pong ball went in front of it, you would see that candle dim. So as it dims, you would go, oh, the only way that can dim is if something goes in front of it. And so if you can observe that like a second time and go, oh, this is how many days it was in between this planet being dim. So here's the problem. So even if you look at this data on 48, you're told that it is a period of 600 days. Well, that's about 2 years, roughly. So you'd have to have your satellite focused on that particular planet. And then you'd wait 600 days and you'd have to focus it back on that particular star to see when it dims again. Okay, so you got 600 days in between. It's like, well, what are we doing in between? Oh, we'll look at other stars. So it's just like one of those deals like don't blink or you're going to miss it. Because it's literally, that light from that star is just going to dim just a little bit. So, again, I cannot emphasize this enough that you understand. When you look at finding masses of planets, masses of stars, whatever those are, we cannot physically weigh these objects. We have to look at the impact that they have on the satellites. We have to look at the impact that they have on the planets that are orbiting them. So, on 48, here's what you need to start with. You need to start with the idea that you have 4 pi squared r cubed equals big G mass times t squared. Now, on the front of the test tomorrow, I'm going to give you the big 3 equations. This one, the one for little g, and the one for velocity, okay, on the planetary side, okay? So, on the front of the test, that's where these equations are going to be, okay? They're going to be in linear fashion. You have to be able to solve for a given variable. So, here's the story. So on 48, this is how this is going to play out. So if you solve this for mass, you've got 4 pi squared r cubed over big G t squared. So you're asked to find the ratio of the star's mass to our sun's mass. So this is going to be the mass of the star for Hg divided by the mass for our sun. Okay? That's the ratio that you want to find. So this is going to be the radius of Hg, period of Hg. And that's going to give you 4 pi squared times the radius of the Earth's orbit, gt squared, and that's cubed. And the period of Earth squared. Okay. So, right away, what can you drop out?
4 pi squared g.
You can get rid of the 4 pi squared g, 4 pi squared g. Those are gone. Okay, you don't have to worry about those because it's a ratio. That's the beauty of it. It's a ratio. So, you've got the radius of the Hg, and because you're told that it's 1.4 AU. What does the AU stand for? Astronomical unit. So that means that's 1.4 times farther from its sun than we are from our sun. So this is going to be 1.4, but that's going to get cubed. Now, you've got the period of Hg, which is going to be, what is that, 600 days? But that's going to get squared, okay? So, this is the only time, listen to me, this is the only time you can leave stuff in astronomical units and days because all you're finding is a ratio, okay? as long as you're working in ratios, it doesn't matter what the units are, they just have to be the same. So then you got the radius of the earth, which is going to be what? 1 AU. But here's where you have to be careful. If you're going to keep this in days, what do you have to use through the period of the earth? Days. You can't make this days and that years. Okay? Because it's a ratio. There are limitations to what you can do with ratios. If you want to make this 1 year, hey, great, fantastic, knock yourself out. But then what are you going to do with the 600 days? Convert that into years, okay? Which would be 1 and some change. I don't care, okay? But just understand that this is a ratio. So, what you should see, your answer to 48, actually for all that complexity, works out to be a very simple number and a horrible GPA. Okay? Works to a very simple number and a horrible GPA. When you get to 49, so this is about a planet, orbits very close at 0.058 AUs from the smallest star. So how long is a year on this world? There's a couple of ways you could work 49. You could set it up as, you start off with this equation and compare that to our sun. Okay? You can do that. The math gets really wonky. Or you could, what I would recommend, how I worked 49, is that I went back to that equation and I took that 0.005 AUs and I converted that into meters, and then I took that 0.13 times that of our sun. I took 0.13 times the mass of the sun and actually plugged in numbers and did it that way. Because that one, you can do ratios, but it gets wonky. Okay? You're going to get the same answer either way, but it just gets wonky. Okay, let's talk about 57. I promise you there's going to be a question like number 57 on the test tomorrow. If you hand in that test and you have not worked one like 57, you have done something horribly wrong. Okay? So, here's what you have to start with. The very first thing you have to realize is that what forces are actually acting on this conical pendulum. So, if you ever play tetherball, it's kind of like tetherball. So, you've got this going around in a circle like this, okay? So you have two actions that are happening. So, number one, you have to identify the forces that are acting on the system. If you don't identify the forces acting on the system, and that's wrong, everything is going to be wrong, okay? Everything is going to be wrong. So, Charles, as this is going around, what are the only two, there's only two of them, what are the only two forces acting on that stopper?
Gravity.
Gravity is going to be pulling it straight down. And?
Centripetal force.
Nope. Thanks for playing. Tension. That's it.
You're welcome.
Okay? Tension. There's nothing else. Okay? There's no squirrels pushing it. There's no wind. There's no air resistance. That's it. Okay? Now, so don't confuse forces with components of forces. Now, Charles, is there a component of the tension that's creating the centripetal force?
Yes.
Absolutely. Okay? So, of this tension, there is a component of that that is creating the centripetal force. Okay? Admittedly, there is. All right? Now, there's also a component of that tension that's balancing out the gravitational force. Okay? That's what you've got. 500 grams, you know, this is 4.9 newtons, which means the vertical component up there has to be 4.9 newtons. That is not the tension, okay? The only way the tension would be 4.9 newtons is if this thing was just hanging here like this. Okay? That is the only way the tension would be 4.9 newtons. But because of the fact that it's going around in a circle like this, not only do you have to overcome the weight, plus you have that additional force of the centripetal force. So here's what you're told. You're told that this length is 1 meter and the radius is 20 centimeters. Okay? So here's the first thing that you got to do. You got to do some trig and find some angles. Okay? There's any number of ways you can set this up. Just be consistent on how you set up the triangle and how you set up that angle. Okay? So here's what you're going to know. You're going to know this side. So the first thing it wants you to find on 57 is the tension on, I think it's tension. Yeah, is the tension of the string. So if this is 4.9, and that's a pretty shallow angle, is your tension going to be bigger or smaller than 4.9? Bigger. It's the hypotenuse. Okay, it's not going to be a lot bigger. Okay, so you know your tension has to be bigger than 4.9. Okay, has to be bigger. Not a whole lot, like maybe like a tenth bigger. Okay, because it's a pretty shallow angle. Now, the answer to B in the book is just completely jacked up. I think they give it as like 30 revolutions per minute, which makes absolutely no sense whatsoever. Okay? So to get that answer on B, you need to go, oh, centripetal force equals mv squared over r. So to do this, again, you've got to go back to the trig, and you have to find that horizontal component of those vectors, okay, because that's your centripetal force. So you got to do trig 3 times. You got to do trig to find the angle, you got to do trig to find the tension, and then you got to do trig to find the centripetal force, okay? Once you get the centripetal force, then you set that equal to mv squared over r. Okay? You know the radius, you know the centripetal force, you know the mass. Find your velocity. So that velocity on 57B should be somewhere between 0.5 and 1 meters per second. Okay? It's not very fast. Then on C, you want to find the period. A couple of things you could do with that. You could take 2 pi r over t. That's what I would recommend, because you just found the velocity from here. You know the radius. Solve for t. Okay? So I promise you, there's going to be a question like 57 on the test. Do the geometry, find the tension, find the centripetal force. Okay? Promise you. Just saying. Promise you. Okay. What other one? On those multiple choice questions 76 through 79, that boils down to one key statement. So it says the spacecraft orbits the moon at a very low circular orbit. So what that means is that here's the moon, here's the spacecraft on a very low circular orbit. What can you assume then is that little g at that point is what's creating the centripetal force, which this is like that minimum velocity to complete a loop, where you can use, then you can use v equals the square root of GER. So on 76 through 79, none of your answers should be B.
Is one of those going to be on the test?
Huh?
Is one of those going to be on the test?
Oh, certainly the concept is, yeah.
Okay.
I mean, absolutely. Absolutely it is. On that other multiple choice question, there's a set of multiple choice questions, 27 through 31. None of those should be B. (27 through 31), none of those should be B. On that question with Lagrange points, I will not make you go through the whole Lagrange calculations, okay? But you need to understand the concept of what, especially that first Lagrange point. Why is it closer to the moon? What would happen if you're on the other side of the Lagrange point closer to the moon? What would happen if you were halfway between the moon and the Earth in terms of the direction of which the net force would point? Okay? So I'm not going to expect you to do all the calculations on 7, but you need to understand the concept of number 7. Okay? On 13, because the 13A is wrong, everything is going to be wrong. Your answer to 13A should be a really, really, really small number, like 10 to the negative 47th small. Okay? Yeah. As in like,
I'll tell Brayden this.
huh?
Oh, that
I'll
was
tell Brayden this.
It's rude.
Yeah,
No.
right?
Okay. Any questions that you want me to go over?
57B, because I got
Wait,
a
what?
lot bigger than 0.5 meters per second.
When you should look for something, I cannot help you.
What you get is the centripetal force.
5 newtons.
No, that's the centripetal force is
Oh,
is the
that was
fat
the
part.
Oh, okay. That makes sense now. That makes sense.
Tyler, centripetal
So, like,
should be a bad.
You need to find the horizontal component of that triangle. That's your centripetal force.
Yes.
okay, so that's why I did wrong.
Yeah. Okay, so if you're done with that assignment and you feel good about it, you can hand it in, or you can hand it in tomorrow. It makes me no difference. But listen to me, Luke Etheridge. This assignment is handed in tomorrow. Okay? If I do not get this assignment tomorrow, I am not grading it. Okay? In any way, shape, or form. Tomorrow. You got that? Okay. All right. Okay.
Cohen's cooked.
Yep.
Or that is.
Cohen claims he hasn't done.
I know he doesn't.
He claimed.
Yeah, well, he's lying to you.
He claims.
That would be the first time in 37 years of education that a student ever lied about having an assignment done.
Really?
What?
That's fitting.
I don't. Of course it's Cohen.
So he might actually have it done. There's a small chance.
Okay.
There's a no
Small
chance.
chance.
There is a chance. So you're saying there's a chance. All right. So there's going to be 2 distinct parts to the test tomorrow. The centripetal motion part and the gravity part. Okay? So let's kind of go back and rehash some stuff on the centripetal motion part. So if you look at these 2 quarters that are on the green spinny thing, okay? So let's start with this. Is it possible for me to swing this rubber stopper around over my head with a constant speed?
What do you mean by speed?
There's only one definition of speed.
Speed.
Yes. Why?
Because speed doesn't have direction.
Speed is just a scalar quantity. Okay? So I can have this thing go around at constant speed, maybe 5 meters per second, whatever that is, okay? Because speed is just how fast you're going. So imagine that you're driving a car and you're looking at your speedometer, and you're driving in a circle, but it's showing 20 miles per hour. So you're driving at a constant speed because your speedometer isn't changing. Now, is it possible for this rubber stopper to go around over my head with constant velocity? Andrew?
No.
No. Why?
Because isn't it always changing?
What's up? You got to get more specific
Or-
than it's always changing, because you know I hate the word changing.
Like, yeah, what Mitchell just said.
What did Mitchell just say?
Direction is changing.
Ah, the direction is changing. So I cannot travel in a circle with constant velocity because I'm accelerating. Now, what's the direction of that centripetal acceleration? At a to the velocity vector. So, as this thing is going around, but this is counterintuitive because the string is taut, right? The string is taut. There's a certain tension in the string. So as I swing this around, is there a force acting outward, pushing on the rubber stopper? Con or S? You were the first to shake your head no. Why?
Because the force is acting inward to keep it going in a circular motion.
Well, but if I let go of it, it goes outward.
Yeah, inertia.
But is inertia a force? No. So don't confuse inertia with a force. So, if you look at the equations that you have on your equation sheet,
Oh, which one?
I think he's getting there, Joel.
There's only one primary equation sheet that we will talk about.
you have v squared over r. That's it. That's all you have. Okay? That's all you have is v squared over r. That's it, nothing else. However,
That's where that comes from.
as that rubber stopper was going around, what could you measure? This is a lab that you all did. What could you measure?
Period.
Period and
Radius.
and you could go, oh, 2 pi r over t equals velocity, which is just a fancy way of saying distance over time. Okay, that's all it is. It's a fancy way of saying distance over time. But again, this is not on your equation sheet. But, oh, it's circumference of a circle divided by t. Y'all have done this countless times. So, could I substitute that in for v?
Yeah.
Yes. And then that's where you're going to get the centripetal acceleration also equals 4 pi squared r over t squared. Okay? Cool. Got that. All I did was take all of that in, simplify it down to this. So, remember, there's a relationship between frequency and period. So remember, you can also rewrite that as 4 pi squared r times frequency squared, and you can write velocity as 2 pi r times frequency. Okay? But again, the only thing on your equation sheet is v squared over r. That's it. That's all you've got. So, I'll post these on YouTube if you want to watch them.
Okay, thanks.
Here, let me give you the reviews. Stop that for a second.